Okay, so I've identified my loop equations. So that outside loop, basically I showed that it was equal to the left loop, and then everything kind of confirmed that. So basically R2's voltage is going to be equal to R3's voltage, which is a parallel rule, which we might have been able to see already. I think I'm just going to take this left loop here, right here, and I'm just going to use that, the voltage equation from that left loop, and I will take that and my known current relationships and see if I can attempt to solve this using just algebra and substitution. Okay, so let's just recreate that just for practice. Let's recreate that voltage loop. I think it'll be just fine. It's pretty easy to do. Alright, so I'm just going to use this left-hand loop that includes the power supply. Okay, I'm just going to go ahead and start from the beginning. 0 equals minus 9 volts as I'm traveling up and around the loop in a clockwise fashion, plus VR1 plus VR2. Alright, so I'm just going to use this loop. I've identified that it really shouldn't make much difference if I use this one or the outside one, so I think it'll be fine. We'll just see how it goes. So one of the first things that I'll do, maybe I'll have it in these terms. So that's 9 volts equals VR1 plus VR2. Alright, so I'm gonna I need to expand my terms and use what I know about Ohm's law to, so Ohm's law, so V voltages, any voltage equals a current times a resistance. So I have some resistances here and I don't know current, although I do have one known current and unknown resistance. So if I expand my terms, that just gives me some more choices to make if I want to make substitution or explore these relationships. So I'll go ahead and rewrite my equation, and I'm going to change my terms into current times resistance. So any voltage is current times resistance. So IR1, just simply whatever IR1's current is times the resistance of R1, okay, plus, and I'm going to do the voltage of R2 as the current of R2 times the resistance of R2. Okay, so in the previous analysis, I figured out that basically this current that goes through R1 was identified to just be the total current. Alright, and then this current that goes through R2, well, we labeled it, or I labeled it as IR2. And then my node analysis here, where this split, I had, what was it? It was I total. Alright, so I got I total coming in like this, IT, and then I had this current here, IR3, leaving this node here. So when I did this node, I created this Kirchhoff current equation, IR2 plus IR3. Alright, and so at that point I didn't actually solve for IR2. Let's just see what that looks like. Well, it would look like this. I total minus IR3 is equal to IR2. Now if you're wondering, like, why am I doing this? How am I thinking about this? Well, I'm over here, if I come over to my equation here, I know 9 volts, I know R1's given, and I know R2, things that I don't know, so I'm just focusing on what I don't know. Well, I've got two things that I don't really know the value of. I've got IR1 and IR2, but I have identified some relationships here. Right, Right, so I total equals IR1, right? So that one I can substitute in, and then I've solved for IR2, and turns out that IR3 is already known. So out of this equation, I mean, I know IR3, I don't know I total, and I don't know IR2, but I can see the relationships, and it turns out if let me just walk through this. So I've got my 9 volts equals, and I've identified IR1 to equal I total. So I'll just say I total times R1. And then in this next term, this is where I might have to think about a little bit more. I've got R2, which is known. IR2 is not known, but using some of my relationships, I solve for it. And what I see is I can replace IR2 with something that I know and something that I don't know. And the key here is that because I've already identified this as going into IR1, and so IR1 and IT are equal, right? So I know IT, or I know I'm going to have to solve for IT, and in these terms where IR2 equals IT minus R3, I've got a known and then an unknown, but it's the same unknown that I've already got. So by replacing this, by substituting it, I will end up with just one unknown. I will only have one unknown in my equation. Let me demonstrate this. So I'm going to take my IR2 and replace it with this substitution. So I'll just put it in parentheses. IT, which is one of my unknowns already, minus IR3, which I know is one of the givens, so just in this circuit it happens to be a nice substitution. And R2 is something that I know. And so now, by doing this substitution, so I replaced IR1 with IT, and I replaced IR2 with IT minus IR3. So now I've replaced my two unknowns with these two terms. So I've got one unknown and one known. So now basically in my final equation, I've only got one unknown to solve for, and I can now solve for I total. So I'm just going to go ahead and do that. So looking at these relationships is the skill that you should try to develop, so that when you get to more complex circuits, you'll be looking at these relationships in that way and trying to figure out what it is that you can substitute for what to, reduce the number of unknowns, or basically just make your life a little bit easier. And it's not really an algorithmic process. You're just going to have to look at the relationships and try to decide which path you're going to take. Alright, so let's go ahead and solve this thing. So let's see. I'm going to run out of room here. So 9 volts equals IT times R1 plus, now I'm going to go ahead and do this distribution and just kind of break all these things up, because I'm going to solve for IT, so I got to get it out by itself. So times R1, so IT times R2 minus IR3 times R2. Alright, so now I've just basically distributed my R2 term in. Now I can see I've got two terms with IT. That's the one I want to get by itself. IV, or 9 volts equals IT. Okay, so now I'm going to factor here R1 plus R2. Alright, so I just factored out my ITs here, leaving me with minus IR3 times R2. Alright, so now I need to add my IR3 term to both sides. Okay, so 9 volts plus IR3 times R2 equals I total, parenthesis, R1 plus R2. Alright, now I can just divide both sides by this R1 plus R2 term, and I've got I total by itself. So 9 volts plus IR3 times R2 equals I total, and I'll do the division now. R1 plus R2. Alright, so I have all these numbers. Let's go ahead and plug in some numbers. So I'll give myself a little bit of room here to work. 9 volts plus 3.313 milliamps times, and I do have R total, or R2, which is 1.8 k ohms. Alright, and all that over 1.2 k ohms for R1 plus again 1.8 k ohms, and that will all equal my I total. So once I find I total, I've basically got enough to solve this circuit using Ohm's law and Kirchhoff analysis, whatever, Kirchhoff's laws. Alright, so let's solve this thing. So let's get the calculator out. Alright, calculator, come on over. Okay, so I'm just gonna type this right in, and we'll just make sure it gets in there right. 9 volts plus 3.313 milliamps times 1.8 kilo ohms. Alright, so I might want to, order of operations says that calculator should like that, all just like that, but just so you can see that, or just to make sure that the calculator and me agree on those, or so we can all see it, I'm just going to put my parentheses in there. Divided by 1.2 e to the third plus 1.8 e to the third, close parentheses. And so all my numbers got into the right spot, and the calculator looks happy. And so my answer, IT equals, let's bring it back just real quick, 4.988 milliamps. Okay, so 4.988 milliamps. Alright, so there's my answer. So now that I have I total, I can find the voltage of R1. I can find, I know I can basically find IR2 and find the voltage of R2, and therefore the voltage of R3. And all of my previously defined equations, I mean, I can just use those to solve all the rest of the values. I can say, well, if I take I total minus IR3, I can find IR2 right now. Let's just do that. Alright, so let's just use this same formula right here. I total minus IR3 equals IR2. Okay, so I just found I total 4.988 milliamps. Alright, minus 3.313 milliamps equals IR2. Okay, so let's just solve that thing. Alright, so IR2, let's just bring that right back. Come on, calculator. So let's move it out of the way here a little bit. Okay, so my I total that I just found minus my given IR3, which was 3.313 e to the negative third milliamps, and so that leaves me with the current for IR2 of 1 1.675 milliamps. So let's just bring that up just to look at it. 1.675 milliamps. Okay. So now basically I know all my currents. I know the current through R2, I know the current through R3, and I know the current through R1. I know the resistance of R1, I know the resistance of R2, so I have enough to figure out those two voltage drops. In the previous, when I was doing my circuit analysis, basically I discovered or rediscovered that, well, in this parallel network, if I know the voltage of R2, I also know the voltage of R3, so therefore I can find the R3 resistance. So I'm just going to switch over to a new page, carry these numbers forward with me, and I'm just going to go ahead and solve the rest of this circuit just so you can see how it all works.